Okay, now we're going to be looking at Faraday's law. So before we talk about Faraday's law, we have to understand the concept of magnetic flux. So the definition of magnetic flux is going to be the surface integral of B through a certain surface. So for example, here we're in a region of space with a magnetic field B. We have some open surface in that space, and the magnetic field lines go through it. So the flux is kind of telling us the amount of magnetic field lines going through that surface. dA is the small surface element on that surface, where the direction of dA will be normal to the surface element. So n hat is a unit vector normal to the surface element. So B dot dA we can write as B dot n hat dA. We do the dot product, so that's B dA cosine theta, where theta will be the angle between the B field and dA. The SI units of magnetic flux are Tesla meters squared, which are can be written as Webers. So to get a better intuition, physical sense of what magnetic flux is, let's look at a few cases. If B and dA are parallel, then theta would be 0 in this case. So our magnetic flux would be B dot dA. So this would be when our magnetic flux would be maximum. Okay, so it's kind of telling us how many field lines are going through this surface. If now we have an angle between B and dA, theta, then our flux is B dA cosine theta. So this is kind of an intermediate situation where it's not maximum, but because we're only counting the component of the magnetic field normal to the surface or parallel to the normal of the surface, count towards the magnetic flux. And then the other extreme is when B and dA are perpendicular. In this case, the magnetic flux is 0. So there's 0 magnetic flux. There are no field lines going through the surface. So now that we know what magnetic flux is, we can go on to look at Faraday's law. So let's look at the same situation that we did last time in last lecture slides. And this time we're going to calculate the magnetic flux through the current loop in the magnetic field in the figure below. So we have the current loop and a magnetic field going into the page. The magnetic flux, in this case, B dot dA, would just be equal to B, the magnetic field, X, one side of the surface within the magnetic field, H, the other side. So that's the area of the surface within the magnetic field. And remember what we do, we move this loop to the right. As we move the loop, the flux is going to be decreasing. There's going to be less of the loop within the magnetic field. So we have d, if we want to know the rate at which it decreases at, d phi dt, we plug in what phi is, bxh. B and h aren't changing. Right? The B field is not changing, h is not changing, but this length of our loop, the part of the loop that's in the magnetic field, x will be changing as we pull the loop to the right. So we have dx dt, which is just the velocity or speed at which we're pulling the loop over. Since x is decreasing, we have a negative v. So our d phi dt is going to be minus vhb. And if you remember from our last set of lecture slides, vhb, that's just what we found for our electromotive force. So what we find is that the induced EMF is equal to the negative change in the magnetic flux per unit time. So this equation expresses the fact that an EMF is induced when we have a changing magnetic field or when the area through which the magnetic field crosses changes. Okay, so a changing magnetic flux produces an induced EMF. So you'll be doing this first problem where you'll have to find the magnetic flux and then the EMF as this loop of wire is moved in different directions with respect to this current carrying wire. And then we'll do this clicker question together. Now we're going to look at Lenz's law. So Lenz's law is going to explain the minus sign in Faraday's law. Right here, the induced EMF is equal to minus the change in flux, magnetic flux. So what Lenz's law tells us is that the induced EMF always gives rise to a current whose magnetic field will oppose the original change in magnetic flux. Okay, so let's take a closer look at what that means. So what it's telling us is that the induced magnetic field is always tries to maintain the status quo. So if we have a situation where we have two magnetic field lines going through this current loop, and we move the magnet up through this current loop, so we increase the number of field lines going through the current loop. So instead of 2, now there's 3. What's going to happen is that the induced magnetic field or the induced current is going to induce a magnetic field that is going to counteract that change in magnetic field that we did when we moved the magnet up. So if we use the second right-hand rule, if we want the induced magnetic field to go down, counteract this extra magnetic field line that we got to go up, the induced current using the second right-hand rule will be in this direction. So you use the second right-hand rule to find the direction of the current that produces this induced magnetic field. We can do the same thing now if we move a magnet down out of the current loop. So initially we had, let's say, 4 magnetic field lines going through the loop. We move the magnet down. So now we only have 3 magnetic field lines. The induced magnetic field is trying to maintain the status quo. It's trying to make it look more like this. So it's going to be going up. That's the induced magnetic field. And then we use the second right-hand rule to say a current going in this direction produced this induced magnetic field. Another way to look at it is if you have a flux that's positive and it's becoming more positive, it's increasing, then the induced EMF is negative, so going this way. If you have a flux that's positive, but it's becoming less positive, it's decreasing, then the induced EMF is positive, so going counterclockwise in this case. On the other hand, if you have a negative flux, but it's becoming more negative, so it's increasing in the negative direction, the induced EMF is positive, so going counterclockwise. And finally, if the flux is negative but becoming less negative, the induced EMF is negative, so going clockwise in this scenario. So we'll do this clicker question together. And the second clicker question. So let's look now at the different ways to produce a current in a loop of wire in a magnetic field. So we have a first experiment that we can do, a first way to produce the current. We can pull the loop of wire to the right through the magnetic field. That would induce a current in the loop of wire. A second way we could do it, we could pull the magnetic field or the magnet to the left while keeping the loop still. So pull the magnet to the left while keeping the loop still. So that's a second way to produce a current in the loop of wire in the magnetic field. The third experiment is we could keep both the loop and the magnet still, but we can just change the strength of the magnetic field. In the first experiment, the loop is moving, therefore the moving charges in the loop feel a magnetic force. That's what we derived when we were looking at motional EMF in the last section. Okay, so this is the case of motional EMF that we studied earlier. In the second and third experiment, the loop is at rest, therefore the charges are at rest, and so they do not feel a magnetic force. In these cases, what is the driving force that generates the current in the loop? So if it's not the magnetic force, it must be an electric field. We know that static charges, even if they're static, even if they're not moving, feel a force in an electric field. So since in experiment 2 and 3, our charges are not moving, it must be an electric field that is making the current, is generating the current in this case. So a changing magnetic field induces an electric field. So let's look back at the definition of electromotive force. The line integral of our force per unit charge, the force generating the current in the circuit. So in this case, the force per unit charge driving the current is the electric field created by this changing magnetic field. Okay, so we put the force per unit charge as our electric field. And we know from Faraday's law that the induced EMF is equal to minus d phi dt. So we can plug those or combine those two equations to get the integral form of Faraday's law. The line integral of our electric field is equal to minus d phi dt. So a changing magnetic field, a changing magnetic flux, gives us an electric field. If we look now at this integral form and plug in the magnetic flux, so integral b dot dA, I'm going to apply now Stokes' theorem to the left-hand side. So we have a line integral of our vector field is equal to the curl, the surface integral of the curl of that vector field. And since this is good for any area, we find that the curl of our electric field is equal to minus the changing magnetic field, d dt of our magnetic field. This is the differential form of Faraday's law. So you'll do an example problem where you'll look at a solenoid and find inside and outside the solenoid the electric field. And that's the end of these slides.